So children, we have been talking about the modern periodic table. We are in the discussion of heading number 7, that is periodic trends in properties. Periodic trends in properties. Now in the periodic trends in properties, we have discussed, we have been talking about point A, the more important, that is physical properties. And in physical properties, we have done number 1, atomic radius, plural of radius is radii, so atomic radii, and number 2, ionic radii. Okay, now just for your extra information, I am going to tell you the atomic radius. We have discussed that. For atomic radius is the distance between the center of nucleus and the outermost electronic shell of an atom, and its trend, how it changes. That in case of normal elements, that is S block and P block elements, which will be our basic focus of discussion. In normal elements, as you go down the group, atomic radius goes on increasing because of increase in number of shells, and as you go across a period, basically what happens is there is a slight shrinkage of the atomic outermost shell, and because of that there is slight decrease in the atomic radii from group 1 to group 17, but in group 18 once again it enlarges because of fully filled electrons, that is fully filled orbitals, and the paired electrons, they give more repulsion, and because of that in group 18 everyone's size is little bigger than group 17. So this is one thing we have discussed. And as far as transition elements are concerned, down the group it will go on increasing for the same reason. Across the period it decreases very little, or you can say it remains more or less same, and the reason is that the last electrons, they enter in the second last shell d orbital, and because of that what happens is there is more shielding effect, and because of that what happens is the atomic radius remains more or less the same. So this much we have discussed, and now after that we have talked about ionic radii, is the distance between the center of nucleus and the outermost electronic shell of an ion, and then the trend in the ionic radii, and then we spoke that cations are smaller than the corresponding atoms, while anions are bigger than the corresponding atoms, and also in the cations, more the charge, smaller the size will be, and in anions, more the charge, bigger the size will be. So between S minus 2 and Cl minus, the S minus 2 will be bigger than Cl minus. Similarly, Mg plus plus will be smaller than Na plus. This much we have discussed. There is one important aspect that you have to discuss is how the atomic radius is measured. So that is also another very important aspect to in the discussion, and that is an extra information I want to give you. Atomic radius, when it is it is measured. So there are 3 ways the atomic radius is measured. That is covalent radius, van der Waals radius, and metallic radius. So there are 3 types. One is covalent radius, valent radius, then van der Waals radius. I'll make little space. Van der Waals radius, and metallic radius. So these are the way they radius. So in covalent radius, what happens is the atomic radius is measured like this. Suppose there is the atom A, there are 2 atoms of A, and they have formed bond by sharing electrons. So they are covalently bonded. So this is atom A, this is atom A. Now what happens is the distance that is taken is between the center of nucleus and this. This is the distance that is taken, and that means in case of covalent radius, the radius that we ultimately measure up is slightly smaller than the actual atomic radius, and there is no other way because they are already bonded, and so you can't separate them and find out. So when they are already bonded, so so it is in this way the distance is measured. All right. And van der Waals radius, what happens is the atoms, individual atoms are all separated each other, which happens in case of inert gases. They don't form bonds. So let us say this is an atom of argon, and this is an atom of argon. This is an atom of argon. Now in this case, what happens is what happens is we find this distance between the two atoms who are attracted to each other by van der Waals force of attraction, and then what we do is we divide this distance by 2, and this will be the atomic radius. Whereas in other cases, in the covalent radius, what happened is we take the internuclear distance of two atoms and then divide it by 2, and that is why it will be this much. But in this case, we take the internuclear distance between two atoms who are attracted to each other by van der Waals force of attraction, and that distance we divide by 2, and that is what will give us the atomic radius. Now how metallic radius is measured? Metallic radius is measured for the elements which exist in the form of metals. Now in case of metals, what happens, children? Let us say this is the crystal lattice of the metal, and please imagine this to be a three-dimensional thing. So these are the metal atoms. Let me say it is monovalent atoms, that is it will lose only one electron like sodium. So what happens is every atom is highly electropositive, and they have got, that means great tendency to lose electron, and energy required to remove that electron, which is called as ionization enthalpy, that also is little less. So as a result, they lose the outermost electrons from the outside. They come on, get lost kind of thing. And when this electron is lost, it is not lost to anybody else. It remains inside the crystal lattice, and now these electrons, they belong to all, or at the same time they belong to none. And these are called as delocalized electrons. They keep on, this cloud is moving around, and they are called as delocalized electrons. These electrons are called as delocalized electrons. So this cloud is delocalized, and every atom will become cation. And in this case, what happens, I will just give you a little idea about the metallic bond also. So what happens is this cation is attracting this electron is attracting this cation like this. So what happens is they all are held to each other by a very strong electrostatic force of attraction, and that is the reason the metals are very strong. And these bonds are non-directional, because the electrons are going on moving around, and therefore you can't say that there is a specific direction in which the attraction is existing. Nonetheless, the attraction exists between the ions and the delocalized electrons who are moving around in the vacant space. All right. And since I have discussed this much, I must tell you, I will also explain to you why a metal is a good conductor of electricity and heat. So when the metal is heated, so all these ions and electrons, they get excited. So they absorb heat, go to higher energy, then they go and collide with the neighbors. And when they collide with the neighbors, they transfer a little bit of heat. Then they get go to higher energy level. So they start vibrating and then go collide with the neighbors. And that is how the heat is transferred from one end to another end. That is one thing. Another thing, the electrical conductivity, how you can explain, suppose this is connected to the negative terminal and this is connected to the positive terminal. Children, from the negative terminal, one electron will enter. I am not saying one, many, hundreds and millions of electrons will enter. This electron will go and push this one, this will go push this one will go push this one, and this will come out. So at any given time, there is a kind of relay race. So what happens is, one is entering from here, one is going from the other side. So it is not the same electron which is moving around. All right. And because of this flow of electrons from negative to positive, there is flow of current from positive to negative. So that this explains the conductivity, electrical and thermal conductivity of metals. Now I will also tell you why metals have got that shine, which is called as luster. What happens is, children, when a light falls on this surface of the metal, the electrons who are on the surface, they absorb that energy and go to higher energy level. They get excited, go to higher energy level, but they can't remain at the higher energy level for long. They want to always come back to the original energy level. हम लोग जिसको बोलते हैं औकात पे आ जाते हैं. And when they come back to the original energy level, so the difference in energy is given out in the form of light, and that is what is seen in the form of metallic luster. That is why on a metal surface, if you put a torchlight, you will find it is shining. But if you put up the torchlight, the shine is not seen. Whatever light may be falling from here and there, because of that the shine will be there. And you will also notice, if the metal surface is coated in the paint, then you don't see that shine. That is because the luster is basically the business of the electrons which are there on the surface. Anyway, I hope you understood got some brief idea about the metallic bond. Now what happens is, when these metallic bonds are formed, so in this case, when I want to find out the atomic radius, so what I will do, I will find the distance between these two kernel, that is two ions, and that distance I will divide by 2, and this will give me the atomic radius of that particular atom. Is it clear to you? So in covalent radius, what happens? The two covalently bonded atoms, we take the internuclear distance and divide it by 2. In case of van der Waals radius, the neighboring atoms who are held to each other by van der Waals force of attraction, which is very weak force of attraction, we take the distance and divide it by 2. And in metallic radius, in a crystal of metal, metallic crystal, what happens is, the two neighboring metal ions, this internuclear distance we take and divide by 2. That is what is called as metallic radius. I hope you understand this. And amongst them, if you ask me, the smallest will be the covalent radius, and the biggest will be van der Waals radius, and intermediate will be the metallic radius. So this is how the atomic radius is measured and discussed. Now we are coming to the point number 3. Last time we have discussed atomic radii and ionic radii. Then I thought I must give you in what way the atomic radius is measured, because you may come across the term covalent radius, van der Waals radius, or metallic radius. This is what you have to immediately visualize. Now I am coming to the point number 3, and the point number 3 I talk about is ionization enthalpy. Ionization enthalpy. Ionization enthalpy. Well, children, what is ionization enthalpy? I'll give you the definition. I'm not writing it, so listen to me carefully. Is the minimum amount of energy required to remove the most loosely held electron from the outermost electronic shell of an isolated gaseous atom. I repeat, is the minimum amount of energy required to remove the most loosely held electron from the outermost electronic shell of an isolated gaseous atom. Now what is an isolated gaseous atom? Isolated atom is an atom which is not attached to anybody else, all alone, so it is isolated. And if it is not attached to anybody else, it will be in the gaseous state. Alright, so I have taken this atom, and I am talking about, let us say, case of sodium, easiest example that you can understand. So I am taking the sodium. So 11 protons in the nucleus. First shell, there are 2 electrons. Second shell, there are 1, 2, 3, 4, 5, 6, 7, 8 electrons, and third shell there is 1 electron. Now out of this, which electron is having minimum attraction from the nucleus, most loosely held electron? It is the outermost electron which will be having the minimum attraction. Alright, and so when I give energy, which electron will come out? The most loosely held electron, which will be obviously from the outermost electronic shell. Now there is an attraction with the nucleus and the electron, and if I have to remove this electron, I have to overcome this force of attraction. And to overcome this force of attraction, I have to supply energy. So I keep on giving energy, gradually I go on increasing the energy. Eventually a value comes when this electron is removed, and I say this is the minimum amount of energy which I required to remove the most loosely held electron, obviously from the outermost electronic shell of an atom which is all alone, that is isolated, and obviously that it could be because it is in the gaseous state, and that is why we say it is the minimum amount of energy required to remove the most loosely held electron from the outermost electronic shell of an isolated gaseous atom. All right. Now this ionization enthalpy, now it depends upon 4 factors. So what are the factors which matters? What are the factors which matters? Now first and foremost thing that will matter is atomic size. Try to understand, bigger the atomic size, more the distance from the nucleus and the electron, lesser will be the attraction, easily you will be able to remove the electron. That means lesser will be the ionization enthalpy. So bigger the atomic size, lesser the ionization enthalpy. Second thing, nuclear charge. So obviously lesser the nuclear charge, less will be the ionization enthalpy. More the nuclear charge, more will be the ionization enthalpy. So if you ask me between sodium and chlorine, who will have more ionization enthalpy? I say chlorine. One of the reasons is chlorine size is smaller than sodium because of gradual shrinkage, and because of that the distance is little lesser, attraction is more, energy required is more. So more the nuclear charge. Another thing is, in case of sodium there are 11 protons who are attracting those electrons. In case of chlorine there are 17 protons who are attracting those electrons. So obviously the nuclear charge has become more and attraction has become more, energy required to remove the electron will become more. The third thing is shielding effect. Shielding effect, I'll just tell you in very simple manner. Shielding effect, what happens is, more the shielding effect, lesser will be the effective nuclear charge on the outermost electron and lesser will be the energy required. That means अंदर अगर electron cloud बहुत ज़्यादा रहेगा तो the shielding will be more, and in that case the attraction enjoyed by the outer shell electron will be less and energy required to remove the electron will be less. And one more thing that matters, and matters a lot, is the electronic configuration. Now what I mean is, if an atom has got electronic configuration whereby it has got only 1 or 2 electrons, he will be very interested in losing electron, and in that case the energy required to remove the electron will be very less. But if an electron has got in the outermost shell 6 or 7 electrons, so in that case its tendency to lose electron will be less. In fact, to gain electron the tendency will be more, and in that case your efforts to remove the electron will be more and ionization enthalpy will be more. So that is why if you compare between sulfur and chlorine, sulfur has got 6 electrons in the outermost shell, chlorine has got 7. Chlorine has got very near to the stable configuration, so chlorine is more interested in gaining electron than sulfur, and therefore chlorine will have more ionization enthalpy than sulfur. So these are the things that matters. Okay, atomic size, smaller the atomic size, more the ionization enthalpy. Nuclear charge, more the nuclear charge, atomic size remaining the same, more will be the ionization enthalpy, more the shielding effect, less will be the ionization enthalpy. And electronic configuration, well, that you have to see. If the electronic configuration is such that by losing electron they attain stability, then ionization enthalpy will be less. But electronic configuration is such by gaining electron they will attain stability, then ionization enthalpy will be more. Now when you come to the trend, so I will talk about in the normal elements, trend in the normal elements, that is what is our discussion. Trend in normal elements, so when I say normal elements, that is S and P block elements, just think of it as you go down a group, what will happen? Distance between the all have got same common outermost electronic configuration. Let us say group 1, all have got configuration of ns1. But as you go down, so what happens, the distance between the nucleus and the outermost electron will become more. So as the distance becomes more, the attraction becomes less, and energy required to remove the electron will become less, and therefore ionization enthalpy will go on decreasing. It goes on decreasing. But when you go from across, from left to right, I am talking only up to group 17, 18 का बात ही अलग है. So when you go to 1, 2, 13, 14, 15, so what will happen, there is a slight shrinkage of the shell, size is becoming little smaller, attraction is become greater, also electronic configuration becoming more and more closer to the inert gas configuration, so tendency to lose electron will become less, so your energy required to remove the electron will become more, and therefore you will find that ionization enthalpy will go on increasing. So I hope you have understood. So basically what I will say, down the group ionization enthalpy decreases, and across the period ionization enthalpy increases, and it will go on increasing, let us say up to group 17, and after 17 when you come to 18, now it has got stable inert gas configuration, then its tendency to lose electron become very, very less, and then we will find it very difficult to remove the electron, and in that case ionization enthalpy for group 18 will become very, very high. That is why group 18 elements, they don't form cations all that easily, and therefore they do not take part in the reaction all that easily. I hope you are clear about what I said. Down the group it goes on decreasing, across the period it goes on increasing up to 17, but after 17 when you go to group 18 ionization enthalpy suddenly increases, right? Now across the period when you discuss, there are some exceptions, and the exception that we talk about is let us say in the second period. In the second period, beryllium, then boron, then carbon, then nitrogen, then oxygen, then fluorine, and then neon. So what do you expect? So I am writing here, what we expect is the ionization enthalpy. With respect to ionization enthalpy, it will be going on from beryllium to boron, it will become more, boron to carbon will become more, carbon to nitrogen will become more, nitrogen to oxygen it will become more, oxygen to fluorine it will become more, and fluorine to neon will become much more, because neon is inert gas configuration. This is how we expect, but in reality it is not like that. In reality we find that beryllium has got higher ionization enthalpy than boron, and nitrogen has higher ionization enthalpy than oxygen. So these are the two exceptions. So what is why? Because this will be explained only and only on the basis of outermost electronic configuration. So children, I take the case of beryllium. Beryllium atomic number 4. So the configuration is 1s2 2s2. Outermost configuration is 2s2 and 2p 0. When you come to boron, boron atomic number is 5. So configuration is 1s2 2s2 2p1. So outer configuration, this is 2s2 and this is 2p1. Is that okay? Now it is found that these orbitals, for their stability, they have got certain tendencies. What is the tendency? These orbitals, they either want to be fully filled, which gives them fantastic stability, or they want to be half filled, which also gives them reasonable stability, or they absolutely want to be vacant, which also gives them stability. They don't want to be partially filled. partially filled orbitals, it doesn't give that much extra stability. So I repeat, they either want to be fully filled or half filled or vacant. Now if you look at beryllium and boron, so what happens is boron might be a little smaller, but in case of beryllium, this 2s orbital, s subshell of the second shell, is fully filled and p is completely vacant. So this gives it extra stability. So you will find it very difficult to remove this one electron from this paired up 2s. Whereas in case of boron, the 2s is fully filled, but 2p is neither fully filled nor half filled nor vacant. So the boron will be very casual about this electron, and because of that, this electron can be lost very easily. And because of that, in a comparative term, energy required to remove the electron from boron will be lesser than in case of beryllium. And that is why you will find beryllium has got higher ionization enthalpy than boron, or boron has got lower ionization enthalpy than beryllium. I hope you got that point. In the same manner, for nitrogen and oxygen, if I write the electronic configuration, you will be able to understand. Nitrogen atomic number is 7. So configuration is 1s2, 2s2, 2p, 3. So this will be 2s2, 2p, 1, 2, 3. Whereas in case of oxygen, it has got atomic number 8. So configuration is 1s2, 2s2, 2p, 4. So when I say it is 2p4, so what happens is, you will find in case of oxygen, the electrons are filled up like this: 1, 2, 3, and here is the fourth one. Then if you look at it, in case of nitrogen, the configuration is quite ideal because 2s is fully filled and 2p is half filled. So it is quite happy with its electronic configuration and it doesn't want to disturb that configuration. Whereas in case of oxygen, if you see, 2s is fully filled, but 2p is neither fully filled nor half filled nor vacant. So oxygen will always have a tendency to lose this one electron, so that it can get 2s2 2p3 configuration, and that is the reason energy required to this electron from 2p of oxygen will be lesser than 2p of nitrogen. So eventually what you find, nitrogen will end up having more ionization enthalpy than oxygen. So that is why nitrogen will have more ionization enthalpy than oxygen. So remember, the certain discrepancies that you find in along the period, they can be explained only on the basis of outermost electronic configuration. Like beryllium having more stable configuration has got higher ionization enthalpy than boron. Nitrogen having more stable configuration has got higher ionization enthalpy than oxygen, and therefore actual trend in the ionization enthalpy, I have written here expected, but actual trend in ionization enthalpy will be boron more than that, beryllium more than that, carbon more than that, oxygen more than that, nitrogen more than that, fluorine, and much more than that is neon. So exceptional cases beryllium and exceptional cases nitrogen. Is it clear to you, children? So that is about the ionization enthalpy and the trend. So what I said, down the group it decreases, across the period it increases, but there are some exceptions like I discussed here, which can be explained only on the basis of stable outermost electronic configuration or unstable or not so stable outermost electronic configuration. Right now, when I talk about ionization enthalpy, I have to know about one more aspect, and there is something called as first ionization enthalpy, second ionization enthalpy, third ionization enthalpy. Now what is that? So let me take the case of aluminium. In case of aluminium, there are 13 protons in the nucleus. So I am talking about aluminium. First shell 2 electrons, second shell 8 electrons, 1 2 3 4 5 6 7 8, and third shell there are 2 electrons in the s subshell and 1 electron in the p subshell. Is that okay? because its outermost configuration is 3s2 3p1. So this is 3s2 and this is 3p1. Now suppose I start giving an energy to remove the electron. So first this p electron will come out, so it will become Al plus. The energy required to remove that electron will be called as first ionization enthalpy. Then any one of them, let us say this one will go, so that will be called, then when this goes it will become Al plus plus, that is called as second ionization enthalpy. And then I remove this one, then this is called as third ionization enthalpy. So energy required to remove the first electron from the outermost electronic shell is called as first ionization enthalpy. Second electron energy required to remove the second electron from the outermost electronic shell of the atom is called as second ionization enthalpy, and third electron when I remove it is third ionization enthalpy, so on and so forth. Now the point is this, if you think of it, which will be minimum and which will be maximum. So ionization enthalpy trend in ionization enthalpy, you will find the first ionization enthalpy will be less than the second ionization enthalpy, and that will be less than the third ionization enthalpy. Now what is the reason? In fact, after first, second will be much more, after second, third will be even more. Now what is the reason? The reason is, so when I remove 13 protons are having attraction on 13 electrons. Now I remove this electron, so that is first ionization enthalpy is gone. Then what happens is, now 13 protons are attracting 12 electrons. So the force of attraction has become much more. You know, the overall attraction on the outermost electrons has become much more because comparative nuclear charge has become more. Earlier 13 protons were attracting 13 electrons, now 13 protons are attracting 12 electrons. So the energy required to remove this electron will be more. And then once I remove this one also, then I want to remove this third, so you can understand the logic. Now 13 protons are attracting 11 electrons, so the nuclear force of attraction per electron has become even more, and therefore for removal of this electron the energy required will be even more. So the moral of the story, that ionization enthalpy, when you compare in a particular atom, the more than the first ionization enthalpy will be the second, more than the second ionization enthalpy will be the third. Is it okay, children? So that is all about the discussion of point number 3, that is ionization enthalpy. The next discussion we'll have is electron gain enthalpy, and that will be in the next video. Okay, thank you, thanks a lot, God bless you.